Right, the resistivity and drift velocity question. Okay, we've got a drift velocity equation. Right, drift velocity is defined as mean velocity of the free electrons in a current carrying conductor. Why is it mean? Let's go to this part of the question first, because this actually will make it more straightforward. Right, so if we have a single electron, okay, which way is it gonna is the drift velocity gonna be? Well, the drift velocity is obviously going to be towards the positive terminal. Okay, that's going to be the mean component of the velocity along the component. Okay, right now draw a possible path. As we know, electrons actually they zigzag, don't they? The overall movement is in a straight line to the left. Okay, now we have an overall average velocity because if we plot a graph of speed against time for a single electron, it actually does this, doesn't it? So it'll speed up, collide, speed up, collide, speed up, collide, but the time between collisions is random, okay, and it keeps changing. Okay, so the actual speed time graph of a single electron could look something like that, but it always drift with an overall average velocity like that, don't they? So if you were to average out all those peaks, if you were to average out all those triangles, it would give you an average drift velocity like that. Okay. Now, calculation. Okay, what have we got? What have we got? Let's write down some values. Okay, we've got, so length, 1.3 centimeters. Immediately get that into meters. We've got cross-sectional area. It's actually calculated for us, so that's quite nice. We're also given, just as it's switched on, a voltage of 12 volts gives a current of 1.2 amps. Okay, so might be quite useful to immediately go, okay, well, R is V over I. So the resistance of the tungsten, when you switch it on, is 10 ohms. That will come in handy because obviously the resistance equation, or the resistivity equation, R is rho L over A. So rearranging this, rho is RA over L. So substituting those values in gives us a quite nice value of 6.08 times 10 to the minus 9. Not forgetting ohm meters as the unit. Right, a short time after being switched on, the temperature of the filament has increased. At this temperature, the resistivity of the tungsten has also increased. With reference to the lattice of the metal, explain why the resistivity has increased. Right, please answer the question being asked, or do what the question asks you to. Okay, so with reference to the lattice, so we have to reference both the lattice and resistivity here. Otherwise, we're going to drop marks. Okay, so just to quickly go through, but at the start, when we first switch it on, we have a high current, don't we? A high current will lead to more collisions or lots of collisions between electrons and the lattice. This leads to an increase in the lattice vibrations amplitude. So let's try and spell this correctly. That's right, isn't it? Here you go. So I've referenced the lattice vibrations amplitude increasing. Okay, if that happens, the resistance of the filament increases. And if the resistance of the filament increases, the resistivity of tungsten increases. So there you go. I've referenced both the lattice vibrations and the resistivity there. Yep. Right, and then finally, suggest why the tungsten filament is more likely to break when it's first switched on. When it first switches on, we have a low resistance leading to a very high current surge at the start. Very high current surge is more likely to burn it out. Okay, I think you might remember me showing you that with the data logger last year. Maybe you don't. Well, there you go, guys. Question 16 done.